So it's a great pleasure to welcome Juna Kollmeyer to give the Origins Colloquium this week. Juna did a bachelor's degree in physics at Caltech before moving to Ohio State for her PhD. She was then a Hubble Fellow and a Carnegie Princeton postdoctoral fellow before joining Carnegie Observatories as a researcher. She has had visiting professorships at the Institute for Advanced Study in Princeton, and recently she was the director of CETA, the Canadian Institute for Theoretical Astrophysics, as well. She's founded the theoretical programs at Carnegie, um, in recent years, as well as being currently probably taking her main time being the director of the Sloan Digital Sky Survey in its fifth incarnation. So it's a great pleasure to welcome Juna. She has a huge range of scientific interests. It's really hard to pin her down in any particular area. So I think we'll touch on that and how that, of course, connects to the great breadth of science coming out of Sloan and these spectroscopic surveys. So welcome, Juna.
Thank you, Jonathan. And I will just turn off my video just for bandwidth purposes. It's a pleasure to be speaking with you guys today about SDSS and beyond. I call it Spectra Ex Machina. And you can see here an animation of some of our robots as a depiction of our robots as they acquire targets on the sky. So I'll be talking today about the Sloan Digital Sky Survey, which has been taking up my cycles for the past decade in large part, and just, starting out what is SDSS-V. So SDSS, many of you may have heard of, and many of you may have even used SDSS data. But what's unique about SDSS is that in astronomy, it's a little bit unique in that it's an experiment that goes on for a certain period of time and then it's over. And it sort of burns itself to the ground and starts over. And so every phase of SDSS is got new sort of scientific focus and new programs. And so this is the fifth phase of SDSS. And the sort of I'll go over the scientific themes of this phase of SDSS, but when I describe what SDSS is, it's really four sort of main components. There's a science survey component, which is obviously the most important thing for for us as we think about what an astronomical survey is. But it's also a dual hemisphere observing facility, which means telescopes and instruments and software. Um, and it's a consortium of partner institutions. And so that's a kind of another entity that it is. And also it's a collaboration of people, of course. So in SDSS, we have over 1,000 people who are part of the collaboration. And I'll go over each of these things in turn. So just on the consortium bit, so we're a global consortium. So we have over 70 institutions spanning 5 continents. We're super proud of this, this aspect of the program. It is, there's not there, as we all know, it's hard to do global things well, and I think that in astronomy we have some good examples of how we can collaborate across um, geopolitical divides, and that's important now more than ever, perhaps. So we're really proud of the fact that that we are able to manage a consortium that spans all of these time zones. Um, in terms of how it actually works, this is just a picture of the org chart of SDSS. Now, that's not something that's typically of great interest, I think, especially to younger people. But I show it here just to kind of indicate that, behind the scenes of what you might see as a data release or internal release of spectra or of images, there's a large number of people that are actually behind the scenes kind of making it work. This is like the unglamorous stuff that every big project like SDSS has. Now, SDSS is a mid-scale project, so that means that it's kind of it's about $100 million project. It's sort of at the scale that you can still make decisions pretty much rationally. So these people all get together and talk, and we don't have a lot of lawyers in the room telling us to do this or that, etc. We just are able to reason our way through to the best decisions we can make. And I think that's something that I really appreciate about the scale of this project, that it is at the sort of rational decision-making scale. But of course, the survey is about science. And so, what kind of science are we doing? So, in SDSS-V, the classic SDSS had a very simple goal, which was to measure 1 million redshifts. And the goal of measuring 1 million redshifts was really to put sort of cosmological redshift surveys on solid footing in terms of large-scale structure, in terms of the distribution of matter in the universe. And I'll go over that a little bit at the end. But by the time we get to SDSS-V, we have realized that, the astrophysics is extremely interesting, and there's a lot of unsolved problems in astrophysics that these types of spectroscopic survey platforms can help address. And so in SDSS-V, we have 3 mapper programs. We sort of organize our science into these 3 mappers. The Milky Way Mapper, and I'll go over these in detail. But the Milky Way Mapper is trying to understand stars. What is the structure of stars? What is their order and multiplicity in life and death? I feel like I don't need to tell this group how important star formation is and how important the stellar architectures are. And what's kind of crazy is that we still can here in 2025 make major progress just by establishing the empirical boundary conditions for these stars. Black holes. In our Black Hole Mapper program, we really want to understand 2 basic questions. So we want to understand the mass function of black holes, and we want to understand how black holes acquire that mass, and so how they're growing. That's what we're addressing in our Black Hole Mapper. And then galaxy formation. Galaxies are, you can either treat them as a cosmological test particle, or you can treat them as something interesting and vital unto itself. And I think my interest is in galaxies, in both ways. But I think that the real trick to galaxy formation is the physics of the interstellar medium and the physics of the gas that both drains into galaxies, but also how that gas is turned into stars or not. So these are our 3 mapper programs, and I'm going to go over each one in a little bit of detail. Again, this is sort of a 30,000-foot summary of the program, which has got I mean, I could give many hour-long talks on each one of these mappers and all of the different science within it, but I'm going to give you just the basic flavor so you have a sense of the kind of scope of the project. So in our Milky Way Mapper, there's sort of a critical leap in SDSS-V compared to previous versions of SDSS. One is that we are really looking at the full HR diagram. So we are really attacking not just little pieces of sort of stellar evolution space, but the entire kit and caboodle. And of course, that's important because we want to understand stars in all phases of their lives, but we also want to, there's just different physics questions in different parts of this diagram that are kind of burning questions. And we don't have even sort of spectroscopic coverage of this. And so in SDSS-V, we're really trying to address that. But the real thing that drives the Milky Way Mapper in terms of like the decisions about what targets we make and the decisions about that has to do with the real revolution that's happened in getting stellar ages. And a lot of that revolution has happened from astroseismology and precision photometry. So techniques like gyrochronology and astroseismology have allowed us to really pinpoint precise ages and then use all of the great tools of machine learning and sort of information extraction to bootstrap those ages spectroscopically. So now we don't need to get astroseismology on every star because we have astroseismology on enough stars at high enough precision that we can label those spectra and propagate those labels forward. And so that ability to do age dissection of the Milky Way motivates our Milky Way Mapper program, and it motivates in particular, our galactic genesis program. And so I just highlight these HR diagrams to show the sort of breadth of SDSS spectra. So this is a slide from Andy Casey, who's the author of our kind of Astra network of pipelines that attack every part of this diagram. But as you can see here, just the breadth of SDSS stellar spectroscopic data is really much broader and different than in previous SDSS phases where had some contaminants in the white dwarfs and you had some giants, but you didn't have this kind of coverage across the HR diagram. Um, in terms of dissecting the Milky Way by stellar ages, I'm just showing an old plot from almost a decade ago, and we have new versions of this plot now. This was 75,000 red giants, in SDSS-4. And so if you can look at this, this is work that Melissa Ness did with her Canon machine learning models. You can actually see that the structure of the temporal structure of the Milky Way is interesting. Is it, you see this younger population and this sort of inside out Milky Way with these older populations toward the galactic center. But with 75,000 stars, you really don't have, again, it's similar to sort of galaxy formation where or large scale structure for the original SDSS. You have hints of substructure, you have hints of smoothness, but you actually, you don't have that robustly. And so in our Milky Way Mapper program, we're actually measuring millions of stars in the galactic disk in order to do this age mapping. And why do we care about age mapping? Well, um, a lot of my background is in cosmological hydrodynamic calculations, and I can tell you that many aspects of those calculations are speculative when it comes to predicting sort of galaxy internal structure. But the thing that's not speculative is when stars form. So if you can get ages of sectors of the Milky Way, it's really a touchstone to calculations on a parameter that's very robustly predicted. So again, SDSS, and interestingly, SDSS has always been run by theorists. It's kind of a thing. Um, and I feel like here the touchstone is really being able to make that comparison with age to the calculations where, both your techniques for machine learning are on very intuitive territory. So we have a lot of we don't have an interpretability problem with these kind of calculations and with this bootstrapping. And also you're in the regime where you're on a very, you're not predicting some element of the periodic table that depends on yields of supernova and depends on a whole bunch of other, just a uncertainty stack that's enormous. You're predicting age. And that's a really, that really gets to what the cosmological calculations are very good at doing, which is the temporal evolution of galaxies. Now, in the course of looking at millions of stars and in the course of looking at them multiple times, you get a lot of sensitivity to binaries. And I mentioned that, stellar architectures are something that the Milky Way Mapper is focused on. And I'm just showing here what type of stellar architectural systems we're sensitive to in SDSS. So for a sort of stellar mass companion, a regular normal kind of star, like the sun, we're sensitive to secondaries that range from sort of black holes and neutron stars all the way down to planets. And so this graph just shows the separation in AU between that secondary and your host star and the secondary mass. And so you can just kind of look at this diagram and say, okay, well, we're not going to be sensitive to Earth's, right? We don't have that kind of mass sensitivity in terms of our radial velocities, but we are sensitive to brown dwarf binaries. We are sensitive to Jupiter, hot Jupiters for sure, and even some cool Jupiters. And we're certainly sensitive to all of the binarity in the compact objects. And that's something that from my work, trying to understand the progenitors of LIGO sources and trying to understand, this in particular, the spin distributions of the LIGO sources, that empirical data point is really important. So just to say that we have very high precision radial velocities for stellar spectroscopic survey, and in fact, Virginia was the sort of epicenter of that. John Wilson at the University of Virginia making the Apogee spectrograph and improving its radial velocity through a number of improvements to the spectrograph in SDSS-V so that we could get radial velocity precision that is in the sub 30 kilometer second regime. Now, moving on to our second mapper, our black hole mapper. Our black hole mapper is primarily using optical spectrographs to map hundreds of thousands of black holes and, um, 1,000 supermassive black holes at very, very high fidelity to do reverberation mapping. So I like to say, from Schwarzschild to to SDSS, right? Of course, the Schwarzschild solution to Einstein's field equations is sort of the first solution that people figure out. And people struggle with this concept for a very long time. And of course, in the late 60s, Don Lynden-Bell makes the connection between accreting black holes and active galactic nuclei. And active galactic nuclei had been observed, from the late 1800s spectroscopically as these high velocity centers of, nebulae. Of course, they didn't know in the late 1800s that the galaxies were external yet. So of course we've come a long way since both Schwarzschild and Lynden-Bell in the sense of, you know, really trying to map out what is the environment around the black hole. So what is the accretion disk, and not just the accretion disk, but the sort of circum-black hole environment, because we know that it's a dynamical environment. We know that there's a lot of interesting plasma physics that is happening in the vicinity of that black hole. And we still would like to understand, there's a lot of mysteries about black hole seeding. There's a lot of mysteries about black hole feeding. In particular, how we get such massive black holes in the earliest phases of the universe. Where are the low mass black holes? All of these questions are critically important to understanding this population of sources. So I like to say in SDSS-V, we're going from sort of snapshots to video, and that we're taking many spectroscopic, the physics is really in the spectra. There's, pictures worth 1,000 words, but a spectrum's worth 1,000 pictures or whatever your resolution is. And so, in terms of this picture of, the sort of circum black hole environment, it's kind of, we have this sort of cartoon picture we've inherited from the sort of 1980s, and we haven't really challenged this picture with the kind of spectroscopic data sets we can get. So we're following up a number of eROSITA sources with multi-epoch spectroscopy in SDSS-V in order to get statistical samples of changing look quasars. They're called changing look quasars because the actual spectroscopic signatures around these black holes are changing in time. But of course, what does it mean to be a changing look quasar? It means that this viewing angle kind of picture has some type of error in it that we're trying to understand, or some type of feature in it that we're trying to understand. So are we sensitive to This is just an example of on the right here, fast accretion flow variations in changing look AGN. This is from an article by uh, Risha Jalton from 2022, and there's updates to this article. But looking at how the spectra actually change in time for a large sample of hundreds of thousands of black holes really helps us pin down these kinds of changes. And of course, looking at reverberation mapping here on the left, looking at the response of the broad line region to the continuum variations of the AGN, give us a sense about the real dynamics and structure around the black hole, and in particular, on the reverberation mapping case, gives a sense of mass. And so we're getting a 10 times larger sample of reverberation mapped masses for in SDSS-V, and that's that many more black holes that have robust masses. Getting the masses of black holes is a real challenge, and so this sample will be have great legacy value in terms of mapping black hole masses to other properties of galaxies and evolution. Just to give you a sense of the survey area, our different black hole mapper targets span the sky. We are an all sky survey conducting observations from two hemispheres, as I'll describe. But just to get a sense of the sort of sky coverage of our reverberation mapping fields here shown in the upper left with those red stars, and our X-ray follow-up shown in the other colors there. Now, how are we doing this? How are we getting this coverage? How are we probing all of these things? Well, one of the things that we did in SDSS-V was we completely revamped the focal planes of both of these telescopes. So the Sloan telescope had previously had had been known for its SDSS plates, and those of you who have seen these plates, they're metal plates where you plug a fiber into a plate, and that's a very labor-intensive process, and you could only put 8 plates up or maybe 10 plates up every night, right? Well, in SDSS-V, we really changed that by roboticizing the focal planes. And that means that instead of having a plug plate and having a person have to plug it, you have these robots that can actually scour the sky and go incredibly quickly. And so that's how we're able to get not a million objects by the end of 5 years, but millions of objects within that 5 year period. So we're really proud of this. This was a very difficult project in terms of the sort of construction and the commissioning, and so we're really proud to be able to have built these and have it deployed and have it working in our sites in at Apache Point and in Chile. And that's what's enabling those two mappers that I was just describing, the black hole mapper and the Milky Way mapper. And to give you a sense of this sort of how much of an improvement that is, if you look at SDSS 1 to 4, so this is all of the plate pointings from the original SDSS Classic survey to SDSS 4 through SDSS 4, you can see the sky coverage is pretty patchy. It's actually pretty tremendous. This figure is not meant to give short shrift to the incredible effort and accomplishments of SDSS 1 to 4, which are truly groundbreaking. But to show you the kind of survey speed and coverage we can get in SDSS-V, I'm showing on the right the target density for the SDSS-V program and our ability to get all sky coverage. And so this is actually what we've been observing so far. And in particular, you can see that in each place there's different numbers of designs that have been done. And you can see that we're actually going over, this is the log of the number of designs done. So you can see that in some cases we've gone many times to parts of the sky. And in fact, doing multi-epoch spectroscopy is one of the, and time domain spectroscopy is one of the things that SDSS-V is really pioneering. So finally, our final mapper here, our local volume mapper. Our local volume mapper is a very unique project. We are really trying to, like I said, try to understand the internal dynamics of galaxies and what regulates galaxies. And to do that, we built an entirely new facility in SDSS-V. So we built uh, a massive integral field unit spectrograph and attached it to small telescopes in order to basically spectroscopically take apart the sky. And so this is just showing the full moon and our local volume mapper IFU. And so you can see that the IFU is about the size of the full moon on the sky. And you can see there are three bundles of fibers that feed three different spectrographs. It's about 1900 fibers in the focal plane, but as you can see, with something of this size field, you can do thousands of square degrees per year. And so the local volume mapper is a massive survey, in particular of the interstellar medium and nearby galaxies. Um, and why do that? And as I mentioned earlier, and I think I don't need to tell many of you in this audience, star formation is complicated, and star formation's like the whole kit and caboodle, right? So we have this very curious fact about galaxies that they are very sort of low. I mean, they're very inefficient. They're inefficiently turn gas into stars. That's a feature of galaxy formation. We know that's a feature of galaxy formation, and we have different models for that energy injection and what are the sources that are suppressing star formation on the sort of cosmological scale. And that is sort of at the level of accretion into the halo and at the level of the interstellar medium itself. But I would say the issue that we have with many of these models, certainly in the cosmology literature, the sort of cosmological simulation literature, is that at the interstellar medium scale, they don't agree on what's going on. And this is not a matter of, building new, if you compare experimentally something like LIGO, where, you need to invent new quantum mechanical mirrors, like we don't have to do that in astronomy. We just have to actually look at the gas and the physical conditions of the gas in order to see what's going on. So that's what we're trying to do in our local volume mapper. We're trying to assess the feedback that's imparted into the interstellar medium by stars and systems by looking at the ISM at the parsec scale where that energy is being injected into the interstellar medium. And instead of doing it in just one spot, we're doing it in 4,000 square degrees in the Milky Way. And in order to do this, we had to build this new facility, which has sort of custom telescopes and spectrographs, and it's sort of a whole new facility at Las Campanas. But the whole point of this is to get that, resolve the gene scale in the ISM and nearby galaxies. So this is the actual facility. This is the sort of, this is the CAD drawings of things, but just to show you that we've already built it. It's up, it's running, it's working. We did this in parallel with our robotic focal planes. And we're super proud of this new facility and this ability to make these measurements. This is showing the extent of the Milky Way, so you can see that picture of the size of the IFU along with the footprint of the survey. We're doing, like I said, 4,000 square degrees in the Milky Way, plus some, kind of targets in the clouds and nearby galaxies, as well as sort of high latitude targets. You can see that we're getting, in Orion, we're getting a spatial resolution of 0.07 parsecs per spaxel. In most of the Milky Way, we're going to get less than a parsec per spaxel. In the Large Magellanic Cloud, we'll get about 10 parsecs per spaxel. And so this type of spatial resolution is the kind of thing that now one can really look at these cosmological sort of subgrid models and ask the question, well, you know, what is actually what, are your models actually right, or are they wrong? So we're providing that connecting data set. And just to show you how that works, this is the Rosette Nebula. And so this is from some of the early data reductions. And you can just see all of those spectra. Every single dot in this diagram is a spectrum. And so this is just showing, the scale of this spectroscopic survey. It's a little bit hard to put into context, but you know, you're basically doing a full spectroscopic map of the sky. And this is the Orion IFU, and these are just some pretty pictures of the site as it was being constructed. Um, I'm going to speed up a little bit here. Another thing we do in SDSS is we're really, mentioned that it's a collaboration. We really, these are pictures from our last collaboration meeting. We're really focused on making sure that young people in particular have opportunities to lead in SDSS. I think that's one of the great things that it as a for so on the right here, you're seeing some of our, speed geeking at our we have a 1,000-person collaboration meeting. How do you get to know people? How do you get to know, younger people who are just entering the field, and so they have opportunities to interact with one another and with senior members of the collaboration. And so we're really proud of having a positive collaboration culture. Now you might be asking what happens to all those plates. Well, those plates have a second life. We actually give our plates to educators in order to help students um, learn about astronomy. So we give plates and we give the designs and we allow them to this is a summer school from Penn State where Neil Brandt worked with a bunch of educators to you see them each with their plate, and then they bring those into their classroom and they have curricula developed around those. And you can teach kids a lot of physics and a lot of chemistry from looking at spectroscopy, but I also like that they see that the physical world is physical, and so they're able to not just interact digitally with SDSS, but also physically. And of course, we also have, it's also, astronomy is beautiful and it's inspiring. So this is from Pacific Standard Time, which is a piece that was an exhibition that was at the LACMA. It's just closed recently, called Mapping the Infinite: Cosmologies Across Cultures, and SDSS played a prominent role in that exhibition. And this sculpture by Josiah McElhaney is permanently on display at the LACMA. In the final minutes here, I just want to kind of, I went very quickly through the science and as well as through the hardware for SDSS, but I want to emphasize this robot revolution that's happening. Robots aren't new in astronomy, but I would say that they've reached a critical threshold where they really can be sort of industrially applied and reliably used in astronomy. This is the DESI focal plane on the left, which has 5,000 robots, and this is the SDSS-V focal planes, the twin SDSS-V focal planes. Now, each DESI robot carries one fiber, each SDSS-V robot carries 3 fibers. So, they're not as different as they might seem. But they have very different purposes. Of course, DESI is focusing on cosmology and sort of that galaxy redshift survey taken to the next level, whereas SDSS is focused on stars and galaxies and black holes and all that messy astrophysics. But because of this robot revolution, it does mean that the opportunity to do really incredible multiplex, incredible speed spectroscopy has arrived. And so you might ask, is there sort of Moore's law for galaxy surveys? And so, we've got SDSS kind of, these are sort of galaxy surveys from 1980 plotted, galaxy redshifts as a function of year. SDSS kicks in at in around the year 2000. We're now at the year 2025, and DESI is well on track. But what happens next? I think these robots are really going to keep us focused. And so if we look at, again, from a theoretical perspective, what we accomplished by getting all of those spectra. If you look at sort of 1980, what sort of thresholds in our understanding of the universe and in our understanding of cosmology did we get by doing all of this mapping? Well, if you look at 1980, there's only a few thousand galaxies that were mapped. You have inflation, which is just really getting developed. You definitely have expansion, but people are seriously talking about galaxies formed explosively in shocks as the main mode of galaxy formation. So our ideas of galaxy formation are pretty immature, actually, even in not so long ago, in the 1900s, as my kids like to say to me. Um, but then with SDSS one, you really get you get the discovery of baryon acoustic oscillations in the galaxy distribution, you get dark matter, you get dark energy, you get all of the gifts that having a massive large-scale structure survey start to give you in terms of the inhomogeneity of the galaxies as tracer particles and what we learn about the underlying physics from that inhomogeneity through time. Then if you look at SDSS 3 and 4, they continue that and we can get all of those same advantages of, dark matter and dark energy and baryon acoustic oscillations, but we can do it purely within the galaxy maps. We don't need any other connective tissue to get estimates for the mass density and get estimates for the cosmology. We can do it just with the galaxies alone. And of course, DESI is happening now. And I think a very super exciting early result of DESI is dark energy, some type of a dynamic field. I think it's still a little bit early to say, but it's just extremely exciting, if breakthrough, if true. But what if we just map them all? Let's just map all the galaxies. That 2060, if we just keep mapping at this speed, we can map them all by 2060. And so, that keep us busy till 2060, which is good, because that'll be around retirement time for me, and so I feel like that's it's a good way to keep yourself busy. And this is the mega mapping era. And so for mega mapping, think about the SDSS focal plane with its 500 robots, each carrying 3 fibers, now moving to 26,000 fiber robots, with robotic fiber positions. And so positioners. You're now feeding 32 spectrographs, DESI spectrographs, and you're using, instead of using a 2.5 meter telescope, you're using a 6.5 meter telescope in Chile, which overlaps perfectly with Rubin. This is a 7 square degree field of view on a 6.5 meter telescope. It's a new optical design that was pioneered by Steve Scheckman, and that we've been working on at Carnegie to flesh out and develop. But this, you can read more about this MegaMapper concept in this archive paper. But this is just to say that this era of just massively multiplexed spectroscopic mapping has been enabled by this robotic technology, and being able to roboticize the focal planes in a precise way that's efficient. And it's an incredibly exciting time. So the idea that we might be able to stay on this very aggressive line of getting galaxy redshifts through sort of stage 5 spectroscopy, which is the next level of spectroscopy, that we're looking at, is just incredibly exciting. And we're thinking at Carnegie of building this new machine, and that's something that we've been working on in terms of the designs. Carnegie, of course, operates the twin Magellan telescope, so this is very much in our wheelhouse at Carnegie. So So I guess that's all, in the interest of time, I think I went over a little bit here. So I'll just stop there and take any questions that you guys might have about SDSS or about mega mapping um or anything else.
Great. Thank you very much, Juna. That was fantastic. So we have time for questions and discussion now, and so we'll just open it up. If people have a question, please raise your hand in the Zoom, and we'll just go through them. I have a whole a bunch of things here. Perhaps you could remind us, Juna, and of course, feel free to keep showing slides as needed.
Sure.
But just remind us on the Sloan 5 data release, because that will of course be of interest to a great number of folks. That's
Yep.
coming soon, is that right?
Yes. So DR19 is coming out this summer. So we are going to be releasing mostly northern data but we are going to also release the first LVM data. If you're at the University of Virginia, if you're a student working with our SDSS-V participants, then you have access to the data already and internal to the collab. And if you want to join the collaboration, it's not too late. We are observing in the Northern Hemisphere through the end of 2026, and in the Southern Hemisphere through mid 2027. So there's still a lot of data, particularly LVM data, in that has yet to be taken. I think one of the nice things about the SDSS collaboration model, is that you can join the project at different sort of membership levels. So for any of you who might be going on to faculty positions, make sure to request SDSS-V membership in your startup package. That would be great. But it's something that it's something that allows institutions to join at different levels. But DR19, which will be SDSS is very much committed to public data and open data. In fact, SDSS was one of the pioneers in providing not just open data, but usable data to the community, to the astronomical community. I think many people think of it as the sort of gold standard in that regard. And I think by the last count is something like 14,000 papers from SDSS data total. And so we are super committed to open data and public data releases. And so please do look out for that in the summer.
Great. So I have a bunch of questions related to some of the science, which I think I'll come to then in a moment. That then we should discuss the plans after Sloan. What you in the sort of immediate future. So that we'll sort of try and divide it like that. But again, if people online here have other questions, just jump in as well. Um, well, you mentioned the age precision as one of the revolutions from astroseismology. Perhaps you could just remind us. So, what kind of precision are we talking about now for, I don't know, if we want to get detailed star formation histories in the Milky Way?
Yeah, so I mean that's always slightly dependent on the target, but you're certainly getting less than a tenth of a dex in age error in the giants, and for the white dwarfs we're actually also doing extremely well. But overall, we're getting uh good. The age accuracy is limited by what has the sort of training, training the good training data. But in our Galactic Genesis program, that does have, that's millions of giants, and so there we are getting really accurate ages. And I think um, you know, I think I think that in terms of the complementarity to simulations, um, I would say that, you know, the the entire question of how galaxy formation is actually proceeding from high redshift to low redshift in terms of our models. We have things that are fitting. We have models that fit integral constraints, but they have size issues. They have sort of hints that maybe something is awry in those models. And I think that's where, and for testing those, you don't need super fine-grained age you know indicators. You just need robust indicators across the whole age spectrum. And so obviously the more fine-grained you get, the better, of course, but if you just want to, we're really trying to test pretty basic ideas about the Milky Way in particular, its formation and evolution from a sort of inside out or not, and how, and in terms of the substructure, like what is that accreted substructure um in the, temporally. So I think like at the level of those questions, for sure the ages are precise enough. And I think that more importantly, just having that really, stellar archaeology is something that we've talked about for a very, very long time. And in particular, the way that we've talked about it had to do with trying to get the ages through chemistry, which is a key sort of component. But if you can tie it to, if you can just have age independently and then look at the chemistry, then that's, I mean, not totally independently, but if the chemistry sits on top of a robust age indicator, then that just puts you in such a better theoretical sort of that puts you in a better empirical test mode, because now the thing that you're resting your comparison on is something that is really robustly predicted in your simulation or your calculation of galaxy evolution. Whereas in the sort of, if you're just trying to do chemical tagging, I would argue that that's a very hard theoretical problem from a you know first principles
Hmm.
chemistry perspective. Like, you just have to get a lot of physical processes correct in a simulation to get that accurate.
Hmm.
um and so you can get gradients, you can do sort of coarse things, you can kind of rely on that, but you're not going to you're not going to trust a cosmological simulation to give you the right, barium to europium distribution in a galaxy. Like that's asking a lot of those calculations, a lot more than they can compute, really.
Hmm.
But if you want to say, you know, are the, you know, when is the bulk of the star form, when are the bulk of the stars formed in the Milky Way in terms of a distribution of ages? When, do we have thick disks at high redshifts? Are stars primarily formed in hot, thick components at high redshift, or are they formed in, accreting satellites that are, on different orbits? Those are the types of questions that we actually can answer really robustly from the calculations, because that's like the zeroth order thing that you're predicting. So
Hmm.
that's where the age complementarity comes in. I think that was a very long-winded
No,
answer
no,
to your.
because you went into actually the next question was the statistical metrics that the simulations can do that can be compared to SDSS data. You mentioned gradients and so on, but one of the things
Yeah.
else is the burstiness of star formation, so substructure in space and time.
Yeah.
And I guess if you have zero point 0.1 dex age resolution, you can begin to constrain this sort of burstiness. I don't know.
Yeah, and I think, I think in terms of the sort of star formation duty cycle, generally, I mean, we are asking the Milky Way to do a lot of heavy lifting in the sense that it's a typical galaxy, and we're expecting, we also though do have a great data set in the Large Magellanic and Small Magellanic Clouds, and so we do have a range of metallicity kind of conditions that, that we're probing. Um, but I always like to say that, well, you know, you don't have a high redshift galaxy, you don't have the conditions of high redshift galaxies locally, across the whole galaxy, but there are patches of these local galaxies that from a density, temperature, ionization structure look very similar. And from a sort of physics perspective, that's really what we care about is that
Mhm.
small scale stuff. So I do think that the burstiness is something that we'll be able to probe. I think I think there's a kind of like this very simple picture of, well, do we just have kind of thick disks at high redshift that then, slowly kind of cool down or get, roiled in hierarchical structure formation at lower redshifts, or do we have um do we have a different picture? I think even those kinds of like much more basic questions can be answered um, sort of directly with the Milky Way Mapper, as opposed to sort of statistically um, uh, and not super satisfactorily. I would say that the problem that we have with our current level of sort of statistical inference is just that um, multiple galaxy formation models can make that statistical distribution fit.
Mhm.
So fitting that data is has now used to be of high constraining power because it required you to, it falsified a lot of models. If your model had a lot of baryons forming stars, then, that model was not going to work with that statistical sample. But in the terms of the internal structures of the galaxies, that's where now we have opportunities to further falsify these models. And that's where our Milky Way mapper plus our local volume mapper in conjunction are really powerful, because you
Mhm.
have the stars, you have the gas, you have sort of all the information you're ever going to get.
Mhm.
Um, for a
Mhm.
galaxy.
So then maybe if we can focus on the young stars, which is more closer to my interest, I mean, how complete is, if we want a census of all the OB stars in the galaxy, how complete are we from Sloan and now, I don't know, within a few kiloparsecs or?
I think we're pretty complete, like within we actually have a program, this sort of parsec sample. So at that, I think we're very complete for the high mass stars, and the young stars, certainly at high mass for in SDSS. I think and Andrew Chachenko is our survey scientist for our Milky Way Mapper, so he's very interested in this. And Marina Kunkel, who's also working on our YSOs hard. Um, I think that in terms of the completeness, um, we're not measuring every O star in the Milky Way, of course. But in terms of having a complete enough sample to do the types of to actually flesh out those statistical distributions, both in terms of the architectures and in terms of the chemical patterns and chemical signatures. I think and by architectures I mean binarity and hierarchical uh, uh, formations. Um, there I think we're doing excellently. So I mean, that was a real focus of the program, and something that is very near and dear to my heart. Of course, there are more stars. We are not, there's hundreds of billions of stars in the Milky Way, and we're not getting all of them. And so it really is a question. And of course, just in the last minute here, um, right now, the AS5 ideas are being thought through, and people are thinking about, now we have this incredible infrastructure. What should we do next? What is the next opportunity to constrain, our theories of star formation or galaxy formation to learn about the universe? And it's not just about constraining these theories, because of course, as you know, when you do a sample of this scale, there's always tremendous discovery space. And in SDSS-V, we just have pages and pages of unknown objects, where we just don't know what they are. Um,
Yeah. Well, no, let's hope we can get as complete as possible on the young stars, and then we really, that's a great data set to test models. Uh, I had a question on the more the black hole mapper side, and one thing that we've been interested in, as you know, one of the big questions is the extent of super Eddington accretion in such black holes. Now it's being talked about a lot. Do you have comments on, with the latest data on better masses from reverberation mapping and basically evidence for super Eddington accretion in any of these systems?
so far we don't, I mean, so I would say that that is something that is incredibly important and something that whether we have that in the can or not, because we've been so focused on acquiring the data that we're pretty, we would love more people to analyze that. But of course, the enthusiasm about super Eddington accretion to solve all sorts of problems in in astrophysics is one of the things we're after. I would say that we are really um a place that we could really use some more cycles, brain cycles, is in those, you know, making predictions from those types of models for the spectroscopic signatures. I think we have evidence in the can of the complicated circum black hole environment, and whether that's the super Eddington or whether that's something else about the accretion disk structure. I would say that the thing that's missing right now is not the data, but the models. And so that's where we really want to see those predictions of, if you have a super Eddington accretion disk, um, what is the spectroscopic signature of that in time? How does that compare to, I mean, how does that, how does that manifest in the multi-epoch spectra? So I would say the answer to your question is we probably do have evidence for that, for whatever that is, in our data right now. But what we don't have is unfortunately, and I would love an army of theorists thinking about black hole accretion disk models.
Mhm.
And I think it would be great to coordinate the community to some degree on that question, on that exact
There
question.
must be people doing it, yeah, so we have to contact them, yeah. Great. And then on LVM, just can you remind us the velocity resolution of the spectra from the IFU in terms of kinematics and dynamics of say H2 regions and
Yeah, so this is something that so the spectrographs that we're using are the DESI copies of the DESI spectrographs. So those are of a few thousand. So in terms of velocity resolution, you're not getting down to, sub-kilometer a second type of resolution. So it's definitely for many of the ISM star formation folks, you would like to see higher velocity resolution than we're probing in the local volume mapper. So unfortunately, if you're looking at like 30 kilometers a second and above, um, uh, you know, type, that's actually in our stellar spectra. So in the local volume mapper, it's higher. It's much higher. Um, so I think that's one of the things that people are thinking about for the next generation, is going to higher resolution, higher velocity resolution in the lines. The
Mhm.
goal for LVM was to really get the different ionization structure. So instead of going for high velocity resolution, going for broad coverage, so that you could actually probe from, with the Rosita, we have the X-rays, so you have that high energy emission, and then going down into that warm ionized gas. And so for that, we chose coverage as opposed to velocity resolution.
Mhm. Well, we're right at this hour here, but perhaps in just 1 minute, what do you see as for the main goal for after Sloan 5 then? Or is that still being defined or?
Yeah, I think so that's still being defined. And the steering committee is being led by Peter Fincherboy and Keith Hawkins. I think I would say that there's I think we have a bit of an embarrassment of riches in that there's these two, these beautiful new focal planes, and we've got Apogee spectrograph, which is still going strong and still very unique. We have LSST coming online. We've commissioned a target of opportunity mode, so it's the first time in SDSS that you can actually take, our entire focal plane is reconfigurable in 3 minutes, and any individual target can be kind of acquired in seconds. And so, this whole time domain mode has been commissioned in the in and that, of course, in the era of things like Rubin and Roman, is very exciting. So, and of course we have the three spectrographs for the northern part of the local volume mapper that we would love to see happen. So I would say that there are many different possible futures for after Sloan 5. And I think one of the things that is important is, it is really community driven. And I think that's very important um, for the future, that we don't just do things because we can. We do things because people really are focused on figuring out the answers to certain questions. And so we'll see. We could probably spend another 4 decades just looking at SDSS-V data. We have a lot of it.
Yes. Very good. Well, we should wrap up the main session here. So let's thank Juna again for a great talk and discussion. So let me stop the recording.